right, well, we'll begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for another weekend just completed. Just pray with us today. Help us to glorify you, Lord, in what we do. And just help us to understand the material, Lord. In your name I pray. Amen. All right, so let's see. I got to, I think last time, the concept of anti-symmetric and symmetric tensors, right? And so I mentioned that if we look at the anti-symmetric tensors, how would those be defined? Remember, so the anti-symmetric let's say type 0p, which would be what? What would those look like? I'm trying to remember, what are the indices on the component? Are they up or down for this one? They're down? Okay. On the components, and then, so this was actually a map from what? What kind of tensor was this? From blank to the reals. What was fill in the blank there? What was it? V cross V cross V cross V. Is that right? Okay. Okay. So then I agree with you and Nathan, and so let's say EI1 tensor EIP. But if it's anti-symmetric, right? What that means then is that you could rewrite this, right, as a sum over, say, multi-indices I, let's say index I an element of Pn. I'll explain what that means in just a second here. And then Ti Ei, where Ei is equal to EI1 sudden my brain has let me down. Curses. Where was that thing? Well, let's see here. I think this is two, obviously. And so what this means is that these are the set of increasing, strictly increasing, of course, p-tuples of indices. So basically that means that the I1 is less than I2, less than less than IP, and of course those are between 1 and n at the most, okay? And then this this so-called wedge product of the basis elements, how did we define it? Like we said, EI wedge EJ was what? EI tensor EJ minus EJ tensor EI, right? And for three things, what do we do? So basically what it's equal to is the sum over ijk of epsilon ijk EI tensor EJ tensor EK. That's a way you could write it. Now this symbol right here, I mean for that to mean epsilon 1, 2, 3 is equal to 1, and then you get a minus for every time you flip an index, right? So like epsilon 2, 1, 3 is minus 1, epsilon 1, 3, 2 is minus 1, and so forth and so on. So what this works out to, right, is E1 tensor E2 tensor E3, and then plus like E2 tensor E3 tensor E1, plus E3 tensor E1 tensor E2, and then minus the so-called anti-cyclic permutations, E3 tensor E2 tensor E1 minus E2 tensor E1 tensor E3 minus E1 tensor E3 tensor E2. So what I'm claiming is that you can use these wedge products to write a basis for the antisymmetric tensors of type 0p. And of course, you could do the same thing with vectors, right? You could look at type P0, and you could just lower the indices rather and take wedge products of vectors just the same, right? Okay. Okay, so the wedge product, it takes on a life of its own. Now we can do this for antisymmetric tensors of type what? Of type 0p, but we could do that for type p equals 1, 2, in fact, all the way up to the dimension of v in an interesting way. Let me just sort of give you some properties of this wedge product that we've so far defined. So one of the things you might notice is that EI wedge EJ is equal to minus EJ wedge EI, right? But that's more generally the case. Like you can see that if you have EI1 wedge EI2 wedge wedge EIP. Let me be a little bit more lazier than that. Let's say, suppose you have E1 wedge E2 wedge EP. Well, that will be minus 1 to the sine sigma EI sigma 1 E of the sigma 1 wedge E to sigma 2 wedge wedge E to the sigma P. Now that guys is just a fancy way for me saying that if you switch any two things in the wedge product, you get a minus, right? But every time you switch two things, you get a minus. So for example, if I had E1 wedge E2 wedge E3, I would get minus E2 wedge E1 wedge E3. Right? But if I flip those again, and so that gives me so the permutation that takes you from 1, 2, 3 to 2, 3, 1, the sign of that permutation is 0. Or what should I say? It's good grief. Oh, I'm sorry, I've written it wrong. I'm an idiot. Not minus 1 to the sine. Sine of sigma. All right, so sine is either plus or minus 1. So the permutation that takes you from 1, 2, 3 to 2, 3, 1, the sign is just minus 1, right? The permutation that takes you from E1, E2 wedge E1 wedge E2 wedge E3 to E2 wedge E3 wedge E1, well, the sign of that is 1 because it has two flips. All right. Now, the thing that's got me all twisted is what's the right way to present the wedge product beyond this? Like, I mean, okay, so this gives us, we've introduced the wedge product as a device to write the basis for anti-symmetric tensors, right? But it's more than that. It takes on a life of its own. You can extend the wedge product past just the basis elements to like extend linearly for the whole space. And the question is, well, what are its properties? Let me just tell you its properties, and then we'll quibble over how to define it. So here are the properties of the exterior algebra. And so exterior algebra over V. So if we have, so the exterior algebra over V is going to work like this. It's going to be, well, let me not get carried away here. Right, so let's let lambda be a P form over V, and let's let mu be a Q form over V rather. Then we have the following properties for the wedge extended. Lambda wedge A mu plus B nu oh, well, we've thrown in another thing. Where is nu going to be from? Where should nu be? If I'm adding them together, you can, yeah, it should be in here. So we can't add apples and oranges. We got to add apples to apples. So let's see here. So, but we can take the wedge product of apples and oranges. It's fine. That's why it's called an exterior product. You take things of different type, put them together, and get things of yet another type. It's an exterior algebra. So this is going to be A lambda wedge mu plus B lambda wedge nu. And the wedge product is associative. You notice that I've been assuming that in the red calculation just above this as well, right? So it's associative, and it has graded antisymmetry. So mu wedge lambda is equal to minus 1 to the PQ lambda wedge mu. Now, I think what I have over here is not, I mean, this actually would not be in lambda 2v. What we're looking at here is something in what? If you go back and look at my, this would be in what? This would be in lambda 2 v dual. Right? And this, I just described something in lambda 3 v dual, because we're taking the wedge product of dual vectors, not vectors there, all right? And we can define the wedge product on either vectors or dual vectors according to our purposes. So I could just as well put v dual here and v dual here, and I'd have the same properties. I would say it's I generally speaking, will say that, so I would actually say that lambda is a p vector and mu and nu are q vectors. If I put a dual here and here, right? If I say then I would say lambda is a p form, and I would say that mu and nu are q forms. That's my typical language. Okay. But of course, we've only really defined at the moment the wedge product for basis forms, right? The thing that remains to define, the question, right, is how do we define lambda wedge mu, really. You see, we haven't really done that. All right, and I don't think, well, anyway. So let me just bite the bullet, write it out for you. This is Manifolds in Differential Geometry by Jeffrey Lee. It's a good book. It's pretty careful. So what he does is he defines the alternating map. And using this alternating map, he defines the wedge product. Here it is. He says that omega wedge, I should say, you just be lazy. Let's see, omega is going to be in here, and that will be in there. I'll change his notation a little bit, but not too much. So omega wedge eta is by definition, according to Lee, you do p plus q factorial divided by p factorial q factorial, then the alternization, the p plus q alternization of the tensor product of omega and eta. This is his definition. Now, what's the alternization of the tensor product is really the question, right? We've actually already been using that, but it's slightly different than what I wrote. So here, alt k of an omega, he defines it by how it acts on v1 through vk. It's equal to a sum, well, 1 over k factorial, a sum over the permutation sigma, the sine of sigma, and then omega v of sigma 1, v of sigma k. This is the anti-symmetrization map. It takes you from type 0k tensors to alternating type 0k tensors. So basically it takes in your favorite k tensor and it anti-symmetrizes it. So this is the definition given in Lee, which will produce these properties. Now, I think it might be interesting, or maybe it's not interesting, I don't know. But Nathan has driven me to this morning because it's bothering me. The first homework problem I asked you, it inadvertently makes you think about how do you interface the tensor product and the wedge product, right? And so this question has arisen. I mean, I have brought this upon ourselves. I mean, I brought this upon us like a plague. Now, so what I want to do is try to flesh out this definition for, let's say, maybe could we try this out for a 2 form and a 1 form, perhaps? So let's let omega be a 2 form on V, and let eta be a 1 form on V, or just a 2 vector and a 1 vector rather. And let's do forms actually. I think it's more natural, because then we'll let them act on vectors, and that'll be all. We'll be happy. I don't need these parentheses. All right, so so in order to we want to calculate omega wedge eta, right? I want to understand what that looks like in terms of tensor products of omega and eta. All right? So let's see here. So apparently we can write omega as what? A sum over I and j, or let's say a sum over I less than j, right? Omega ij, good grief, ei wedge ej, right? And we can write eta as a sum over k of eta k rather, ek, right? Maybe it's healthier for me to write omega as a tensor. Let me do that, okay? Can you forgive me? Let's just say a sum over I and j. Of EI tensor EJ. So of course omega ij has a certain antisymmetry, the components. Now then what? I need to figure out what is alt, right? Well, apparently 2 plus 1, right? Of omega tensor eta. What's that look like? So I let that act on what? 3 vectors, right? Say v1, v2, v3, right? And that's going to be the sum, what? It's 1 over 3 factorial, right? And then we have this sum over permutations, right? There's 3 things. I can write them out. It's not pleasant, but I can write it, right? What are those 3 things? We got the ones I just wrote over here, right? The plus ones, the 1, 2, 3, the 2, 3, 1, the 3, 1, 2. So I have sorry, this is slightly confusing because I've used omega in 2 different ways here. The omega is actually omega tensor. So I need omega tensor eta acting on, well, v1, v2, v3, and then the same for 2, 3, 1 plus 3, 1, 2, and then minus 3, 2, 1 minus 2, 1, 3 minus 1, 3, 2, right? Yeah, the same thing, but with 1, 2, 3 replaced with 2, 3, 1, and so forth, right? So what that gives us is 1 over 3 factorial, otherwise known as 6, but I'm going to leave it as 1 over 3 factorial. And then we've got like omega, right? So if you look at that gives you omega of v1, v2, and then eta of v3, right? Because omega tensor eta acting on a set of vectors x, y, z is equal to omega of x, y, eta of z. That goes back to the definition of the tensor product acting as in terms of multilinear maps. And I mean, I can break this down further. Omega is a sum. It's this, right? So if you let omega act on x, y, then you get ei of x, ej of x. But that, I mean, it goes back to this formula basically, and the definition I gave for how the tensor product of dual vectors acts on a tuple. I think that's okay. So I get omega v1, right? But then I get the same for what? You know, like these other, right? Until I get to minus omega of v1, v3, eta of v2, right? Now, omega of v1, v2 is equal to minus omega of v2, v1, right? Because it's anti-symmetric. So if you look at this, there's 2 things that you can kind of like group I think, for example, this one gets attached to this one, right? But what happens? If you want to make them the same, you have to flip the 2 and the 1, right? Flipping the 2 and the 1 puts a plus here, right? So I can just write 2 times that. And then what? Plus 2 omega v2 v3 eta v1, right? And then plus 2 omega v1 v3 eta v2. Is it anything? I don't know. I mean, yep. I'm trying to think of how can I mean, okay, that's a calculation. We did it. And then what do we have to do? What else is out here? Is this factor, right? So then we multiply this by what? P plus q factorial is what here? 2 plus 1. So we multiply by 3 factorial divided by 2 factorial times what? 1 factorial, or just 2 factorial. So the 3 factorial, so you see what happens? The 3 factorials cancel, the 2's cancel, and you're just left with what?
Well, there's pretty much those 3 terms.
Yeah. Yeah. So that's the wedge product of that 2 form and that 3 form. Excuse me, that 2 form and 1 form. So I think, Nathan, to answer the question that you were asking, so what Nathan had done, which is understandable because I didn't give a definition yet, the thing that you're kind of left out in the lurch for is like, how do you take EI wedged with something like, EJ wedge EK, right? Like, how is that defined? Not that, but oh man, what was it? Curses. The thing is, I only gave you the wedge product for a basis. I didn't tell you how to take it between just different basis elements itself, and so this is that definition. Uh-oh. Is there a question, Daniel? Now, I'm going to stop here for now on this. I'm thinking about it some more. If I have some more to say about it some other day, I will. All right? But the takeaway message is that these are the properties of the wedge product. It distributes across addition, it's associative, and it's graded commutative. All right? These are the mission critical facts, let's say. And also, we can build any anti-symmetric tensor using the wedge product as a basis, right? But the interesting thing, of course, is that the basis itself takes on the structure of an algebra. What's an algebra? An algebra is a vector space paired with some multiplication. It's not that the vector space itself is an algebra. It's actually, but we say it's an exterior algebra because, like, if you look at this, one of the things we can say is that if you had any basis element like repeated, what would happen is you'd get 0, right? Because if you just flip the basis element with itself, you get minus the same thing back again, right? So any basis element for V repeated gives you 0 from basically, I mean, this property, if you like, or just the defining. Depend. I mean, we're starting to get into a chicken and egg situation. I won't commit to what the definition is. All right. because I'm not convinced that this is probably a good definition here because it's general, right? And this, if we made this the definition of wedge product, then we can take this and we can go back and construct those, right? So this is probably a good definition to actually take as a general definition. That said, you can then ask the question, what are the possible p vectors over a vector space of dimension n, right? And so the convention is this, is that this lambda v is equal to the underlying field, let's say, I'll just say reals, but you could do complexes, and then direct sum with the dual, direct sum with the two vectors. Oh, I'm sorry. Well, I'm going to talk about p forms. So let's say the exterior algebra over v dual. So reals, direct sum v dual, direct sum the two forms, direct sum the three forms, and so forth. Direct sum the n minus 1 forms, direct sum the n forms on v over v dual. That's the only non-trivial things this wedge product brings you to. But you can take an arbitrary element in here, let's say homogeneous. In other words, it's just of degree 3 or just of degree p or whatever, and another one of degree q. And when you wedge them together, you get a p plus q form, right? But if p plus q is greater than n, it just wedges to 0 because there's some basis element repeated. But otherwise, if you take the wedge product of two things in here, you get back to something in here again. And if you can define it from just, say, p on q, you can extend linearly to do the arbitrary linear combinations of, you could take a sum of 1 forms and 2 forms and 3 forms, take a wedge product with a 2 form, and you'd get something that's like 3 and 4 and, 6. And but usually we just work with homogeneous forms, in other words, forms of definite degree. Like, you don't find yourself working too much with like the sum of a 1 form and a 2 form. But technically speaking, that could be defined in this space. But that said, we work with the homogeneous forms most often. So the point is that this is an exterior algebra because you started with an n-dimensional space, but then you've got all of these different things, and the wedge product takes you between these different things, and the 0 forms. So this is the reals. The 0 forms are just scalars, right? And this is the one forms are just the dual vectors, all right? Any questions about this? We could count here what are the dimensions of these different spaces, right? That becomes a question of how many ways can you choose. So for the p forms, it's a question of how many ways can you choose p distinct increasing sets of indices from n indices, right? So like, what's the dimension of the p forms? So we're choosing p distinct elements from n distinct elements, let's say. Suppose the dimension of v is n. So by the way, these properties can be proved by a concrete, albeit tedious, calculation from this definition. Let's see here. Let's give a specific example. Maybe that'll help. It's not quite p factorial. So for example, let's look at n equals to 3. So here I've got v dual is the span of E1, it's the span E1, E2, E3, right? So what are the 2 forms on this 3-dimensional? So we could do E1 wedge E2, E1 wedge E3, E2 wedge E3. That's That's it. Those are the distinct pairs I can pick from 3 elements, right? How about 3 forms? There's just one of those. What if we had n equals to, say, 5, and you looked at so you got what? You got E1 wedge E2, E1 wedge E3, E1 wedge E4, E1 wedge E5, E2 wedge E3, E2 wedge E4, E2 wedge E5, E3 wedge E4, E3 wedge E5, and finally E4 wedge E5, and we're out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say again? 5 choose 2, yeah. In fact, that is generally the case, that this is n choose p. It's the number of ways you can distinctly choose p things from n things. Can I say it more carefully, Nathan? Is that right? I don't teach probability, so like if I was butchering the meaning of choose, I wouldn't notice. Okay, good. So the point here then is that this is actually, each one of these has the dimension given by a binomial coefficient, right? And if you add them all together, the dimension, and so sometimes this, I think Brentland uses that. Some other people would say that this is omega of V dual, so it's the total exterior algebra. The dimension of that is actually 2 to the dimension of V. That's what's generally true. And so like in 3 dimensions, what's the 0 forms are 1-dimensional, right? So above this you've got lambda 0 V dual, which just has basis. It's very boring. It's 1. So you've got 1 plus 3 plus 3 plus 1, 8. Yeah, the binomial coefficients always give you the dimensions of the different. Now, you also know from Pascal's triangle that there's certain symmetries between different binomial coefficients, right? Like, it's no accident that this is 3-dimensional and this is 3-dimensional, right? You could also look at, let's see here. So if I 1, 1, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So you can see that there's a symmetry here between choose 2 and choose 3. So in fact, lambda 3 V dual, which would be the span of what would it be? E1 wedge E2 wedge E3 E2 wedge E3, E3 wedge E4 wedge E5. I don't want to write them all out if you don't mind. These are both 10-dimensional spaces. There's this pairing between P and n minus P forms. All right? This isomorphism that I'm mentioning is called Hodge duality. Hodge duality is the isomorphism between P and n minus P forms. It's most simple when we view it in terms of an orthonormal basis. If I use a coordinate basis, it gets cluttered with the determinant of the metric and some stuff, which we'll get into some other day, but not today. So that's Hodge duality. Now, you know what? Let me just kind of bring this stuff back down to earth. Let's take 10 minutes or so, and just explain how this works out in 3 dimensions. Now, some other semesters I might have made this a homework problem, but I feel like I've been doing things of such arbitrary degree, I owe you something like a little bit more concrete, so here it is. Can I steal your markers, Lorenzo? No! What's that? You failed me for the last time, Lorenzo? What's that? I will need a marker that works shortly. These are getting dry. I forgot to bring markers. Okay, so in 3 dimensions. Green and blue, I'll take it. The Sharpie? Well, I'm not sure I want to commit that much to this lecture. So V equals R3, all right? If you look at that, we have a tower of things. If we look at the 0 forms on V, we have reals, right? If we look at the 1 forms over V, we get, and I usually like to think about the forms, not the p vectors. So 1 forms on V, of course, would be R3 dual, right? And the 2 forms on V would be, well, I just wrote them over there, right? So, let me not rewrite that. I just wrote this. Why am I writing this again? Let's look at V equals R3, and let's study the exterior algebra over V dual for this, all right? So there are 2 fundamental maps, right? The one is that if you give me a vector, say ABC, then I can associate with that the 1 form associated with ABC is equal to like A E1 plus B E2 plus C E3. Right. Or if you wanted a more compact notation for this, well, that's fine. That's fine. Now, if you're, and likewise, we can define the so-called flux form. This is the work form. The flux form mapping, ABC, will be equal to A E2 wedge E3 plus B E3 wedge E1 plus C E1 wedge E2. Now, I realize that this is a violation of our typical choice of ordering, but it's a necessary one to make natural contact with vector calculus. So these are 2 different, so we can either associate to the vector a 1 form, or we can associate to the vector a 2 form, because they're both 3-dimensional objects. And here's the really cool thing. If we calculate omega of vector A wedged with omega of vector B, what we get, if we work it out, is the flux form, all right, of, well, let's work it out. So we got A1 plus B2 plus C3 wedged with, let's say B is XYZ. So we got AX E1 wedge E1. Actually, if you don't mind, I'm not going to write this down. This is the last one I'm going to write down, because what's E1 wedge E1? 0. So we don't need to write those terms. We should just collect together. We got like A, Y, E1 wedge E2, right? Plus B, X, E2 wedge E1, plus A, Z, E1 wedge E3, plus C, X, E3 wedge E1, plus A, oh, that's it for A, plus B, okay, thank you, plus BZ, E2 wedge E3, plus C, Y, I think, E3 wedge E2. But then if we just rewrite this, we've got ay minus bx e1 wedge e2 plus cx minus az e3 wedge e1 plus bz minus cy e2 wedge e3. So this is exactly, if you take A cross B, this is the first component of that. This is A cross B. The second component, this is A cross B. The third component, where I'm saying that A is equal to ABC and B is equal to XYZ. Oh man, yeah, thank you. Goodness gracious. That's the third, yeah, thank you. That's the third component. That's the second component. Okay, so I was 33.333% right. Or if you give me some partial credit on this all up here, I was more like 80% right. Depends on how the partial credit was allocated, but anyway, the point is that that is exactly the flux form mapping of the cross product. So the question that you guys will ask once your instructor gives you time to think is the wedge product the cross product, right? I mean, they look a lot alike. But the answer is no, they're not the same thing. They're related, but they're different. The wedge product, by its construction, is built from the tensor product, and the tensor product is associative. That associativity is inherited from the tensor product in that definition. So the wedge product is associative. The cross product is not associative. A cross B cross C doesn't make sense. I have to say A cross B cross C, or A cross B cross C. You know, the ordering of the cross products matters. But here, this is the connection, right? And you see that the cross product is really a weird thing because it's you know, it takes, I mean, there's apparently our way of thinking about vectors, right? It's muddled because we're really from the viewpoint of where we are now, you could say, well, vectors are really two different kinds of things. There's the vectors which are like one forms, and there's the vectors that are like two forms. But we're just using vectors in Calc 3 for all of these different objects, right? So we're abusing this isomorphism between two forms and one forms in 3 dimensions in Calc 3 without even realizing it, right? And that's why we do so many different things with vectors in Calculus 3, right? From the perspective of calculus with differential forms, we use one forms for one-dimensional things. We use two forms for two-dimensional things. And so that you'll see how that is. Eventually, we'll learn that when you elevate these to like vector, to like not just one point, but a whole field of things, you integrate a one form along a curve. And that will correspond to the line integral of a vector field. We'll integrate a two form over a surface, and that will indeed correspond to the surface integral. But you can't calculate a surface integral and a line integral of a one form. One forms go with one-dimensional objects. Two forms go with two-dimensional objects. There's this natural pairing between k-dimensional subsets, manifolds rather, of space and the k-forms that are built over said subsets. All right? Now there's more. What's the Hodge dual? If you look at the Hodge dual of the oh, well, I should save that for another day, but it turns out that the Hodge dual of this is the flux form. So flux form takes you back and forth between work form and flux form. So like Hodge dual of omega A is the flux form of A, and vice versa. Exploiting that isomorphism. But I haven't written it down carefully yet, so let me just stay away from saying more about that. Let's go back now to something I advertised last time, which was that we could derive properties of determinants using the wedge product. I think this is a really neat calculation I'm about to show you here. I have more to say about this as we go on, all right? We'll come back. We'll make an explicit dictionary between calculus in 3 dimensions and this new world of the exterior algebra. Oh, I guess one more thing we could say while I'm on this, though. You could, so this is more later on this, all right? This much we could do right now. I need a space. What would omega A wedged with the flux form of B be? So it's what? It's A dot B? Yeah, you can see it, right? You guys saw it. It's A dot B times E1, wedge E2, wedge E3 in our current notation. Yeah. So once you know that, then you know that the omega A, wedge omega B, wedge omega C is what? It's A dot the flux form of BC, which is B cross C, so there you go, dot product, triple product, cross product, it's all in the exterior algebra. Just look at it. It's all there. Are we good? Now, the most significant gap in my presentation right now is the fact that I have not connected this explicit definition I gave for you with the actual properties I claimed for the wedge product. Right? That's a significant gap in the exposition, one I may not fill because I think it's tedious and it may not be that enlightening to you. It's not currently in the homework now. Not on purpose anyway. If I've asked something which scratches that itch, you should come and talk to me about it because maybe I didn't intend it. Pth exterior power so I want to look at a linear transformation from V to V. I want to talk about how you can extend this to a linear transformation from P vectors to P vectors. All right, so you can definition. So you do have a homework problem on this one. So the Pth power of T, it's a mapping from P vectors to P vectors, like that, all right? And how do you define it? The definition is that if we feed the Pth exterior power of T a typical V1, wedge V2, wedge wedge Vp, what's it defined to be? It's defined to be T of V1, wedge T of V2, wedge wedge T of Vp. So you simply define it to be the wedge product of the outputs on the P vectors which are being wedged. Yeah. And then you extend linearly, right? Right. Generally, vectors in lambda PV may be linear combinations of such P vectors, right? May or may not be possible to decompose a given P vector into just a wedge product of just P vectors, I think. That's actually kind of a hard question, right? Is it always possible to take two things that are like this, right? Two things that are P vectors and combine them into a single wedge of P vectors, right? If I had V1 wedge V2 wedge VP, and if I had let's say W1 wedge W2 wedge WP, is it possible to rewrite those, the sum of both of those, as, say, U1, wedge U2, wedge wedge UP, where U is somehow built from the V and W. Anyway, that aside, doesn't matter. We extend linearly, all right? And what are the properties of this pth exterior power? Well, your homework, all right? So first of all, it's linear because we defined it on a basis. We do know that these form a basis for the p vectors that I've essentially shown in the last couple classes. But so extending linearly makes it a linear transformation. What are the properties of it? Well, what if I had two such things? What if I had lambda p t of lambda ps, right, acting on v1 wedge wedge vp. This is kind of irrelevant. Let me just call this thing x. I already wrote it. Fine, it's done with. That is in fact equal to the pth thing of the composite, t composed with s, the pth power of the composite acting on that. I mean, the element in the p vectors is just riding along here. It's not playing an interesting role. The point is, this pth exterior power behaves naturally under composition. That was one of your homework problems. What was the other? Do you guys remember? The other thing I asked you to show is, let me see here, and whenever you're asked a homework question about about p-forms, you are certainly welcome to use the properties of p-forms to do it. I don't expect you to go back to the definition. If you could, I would like you to avoid going back to that definition if at all possible. We'd like to work from the properties of differential forms I wrote today. So if we look at the p plus qth exterior power of this being a p form, this being the p vector, this being a q vector, then it in fact is equal to the pth exterior power of t acting on lambda wedged with the qth exterior power of t acting on mu. So what happens when we look at, for example, the end? What do the end forms look like? If we look at the end forms on V, what does that look like? Right? That's the so-called top form on the vector space. There's just one of them. If you have anything beyond that, you got to repeat, so it's 0, right? So that's the highest form that you can build over the vector space. So if you look at then the nth exterior power of t, right, acting on, say, E1 wedge E2 wedge wedge En, I mean, that's about all there is to work on, right? What will this be equal to? Well, by definition, that will be t of what? T of E1 wedge t of E2 wedge wedge t of En. But what is that?